Hi, welcome to lecture 13 of ECE 141. In this lecture, we will be talking about cyclic codes. So what are cyclic codes? In the previous lecture, we talked about linear block codes. And linear block codes are used for error detection and error correction. We've shown you examples of a 1-bit error correcting code and a 3-bit error correcting code, and we characterize the probability of bit error of the correcting codes, and we compared the power needed for an uncoded BPSK versus a coded BPSK, and we've shown that for that specific example you have some form of coding gain due to your error correction. Coding gain is actually a metric for of the performance of your code. Alright, so what are cyclic codes? Cyclic code is also a linear block code, so it's a subclass of linear block codes. Therefore, it also has the properties of a linear block code. But the difference is that cyclic codes are easy to encode and possess some mathematical structure that makes it easy to encode. Of course, the properties of the cyclic code is similar to your linear block codes, in which it's linear. The sum of any two valid code words is also a valid code word. Okay. Cyclic property is a different one. If you perform a cyclic shift on a valid code word, the resulting code word is also a valid code word. Like, for example, if you have a 7-4 code, okay, so 7-4 code with code word like this, if you shift the most significant bit to the least significant bit, you'll end up with this combination of bits, which can also be a valid code word if your code is cyclic. Okay, so to generate cyclic codes, you'll need to use polynomial representations of the bits for your generation. So just note that the polynomials are from the Galois field 2. Okay, and it's as you recall, it's a finite field, as what we have been discussing for the linear block codes. Alright, so first, how do we represent, just a refresh, how do we represent the message and the code word as polynomials? So if you're given a generic series of bits, you can, as you know from linear block codes, you can represent them as matrices or vectors. Okay? It's actually easy to create a polynomial out of them. The most significant bit would have the variable with the highest power. The next one would have the highest power minus 1, and the least significant bit would have no variable x right there, or x raised to 0, which is 1. Okay, so this is how we represent a series of bits into a polynomial. So let's say this series of bits is a code word, a valid code word C of length n. Okay, suppose we multiply x to this code word right here. So let me illustrate that with an example. Let's take the code that we got earlier, 0110 110. Sorry, it's not that. Oops, it's actually okay. 00. Sorry. It's 0110011. There you go. So we take this code word and multiply it by x. By multiplying it with x, we're effectively shifting or inserting a 0 at the end of the code word. Okay. The polynomial representation of this series of bits will be divided by the polynomial x to the n plus 1. Okay, if you divide that by x to the n plus 1, you will be left with this c sub n minus 1 rather, plus some polynomial c1 of x divided by your x to the n plus 1. This c1 of x satisfies the cyclic shift. Okay? So this will now be the cyclic shift of c of x. Okay? That would mean that we are going to discard the most significant bit and we'll end up with the cyclic shift version of the code. So that is the result that you see right here. So it's a cyclic shift of the original code word that we used. Okay. So how do we generate code words? If for linear block codes, we have generator matrix, and to check if that code is valid, we have the parity check matrix. For cyclic codes, we have the generator polynomial. The generator polynomial has an order n minus k, which will form an nk code. That would mean that your g of x should have a degree n minus k. If its degree is n minus k, then the coefficient of the most significant bit should be 1, as you see right here. And the others are all arbitrary, except for the last one, which should be plus 1. Okay. So let u of x be a message polynomial, okay, with length k. It's a message polynomial. A valid code word is if your code word is basically divisible by g of x. So that would mean that if we take the modulo of c of x by g of x, it should be equivalent to 0. And the easiest way to generate a code word is simply by multiplying your message bits or your message polynomial by the generator polynomial g of x. Okay. So how do we check then if a code word that we received is valid? Okay. As you know, as I've mentioned before, a cyclic code must have the cyclic shift property. Okay. Cyclic shift property, then recall that it's this. You multiply x to your code word c of x and divide that by x to the n plus 1. The remainder will be the cyclic shifted version of your original code word, and this must be divisible by g of x. Okay. For your cyclic shift property to work, your generator polynomial must be a factor of x to the n plus 1, so your cyclic shift property will work. Okay. So the degree of g of x is the number of the parity bits, as you recall, and n is the total number of bits per code word. Then we can actually get the parity check polynomial. That is the parity check polynomial satisfies this property or this equation, where your parity check polynomial, quote unquote, completes the generator polynomial. So if you multiply the generator polynomial to the parity check polynomial, you'll end up with x to the n plus 1 right here. Okay. So this h of x is used for, well, parity check. Right? So it will be used for detecting and correcting the codes. Right? For example, consider a code of block length n is equal to 7. That means the factors of x to the 7 plus 1 will generate your cyclic codes. That's from this property right here, that g of x generator polynomial must be a factor of x to the n plus 1. So let's get the factors of x to the 7 plus 1. It's equal to this, this, and this. You can't use this because the degree of that is less than 3. Okay? And if you use this, then the code that will develop is 7, 5. Okay. Sorry, 7, 6 rather, a 7, 6 code. But we want to generate a 7, 4 code. That means we'll use the factor that has a degree equal to 3. Okay. So we'll use this generator polynomial, x cubed plus x squared plus 1, or this x cubed plus x plus 1. So those are the two considered generator polynomials. And a valid code word is divisible by g of x, so quite simply we multiply all the possible message polynomials by g of x. Okay, so with having 4 bits given by 7, 4 right here, 16 possible code words can be generated. So let's see. So the first 8 is given by this table. Okay, first 8. So the polynomial representation of 0, 0, 0, 0 is 0. This one is this one, and so on and so forth. Right? So you can get different representations of the polynomial, and quite easily just multiply u of x with g of x. You'll get the code word polynomial, and that can be easily converted to your code word vector. Okay? So you see here. So just get the weights of, or the coefficients rather, of your different variables. Okay, so the next 8 is given by this. Okay, so as you can see here, you have 1, 0, 0, 0, which is x cubed. Multiply that by g1 of x, you get a code word right here. So notice from these two, if you perform a cyclic shift, no, not this one, that's easy. If you perform the cyclic shift from here to here, right, you end up with the code word that you see below, and you do a cyclic shift again, you end up with the code word right here. Another cyclic shift of that, it's this code word. Okay, oh sorry, rather it's this code word. Right? And you do that for the other code words, you will see that all the valid code words will have the cyclic shift property that I mentioned earlier. So since your cyclic codes is a linear block code, a generator matrix can also be developed. Okay, so recall that a generator matrix for an NK code can be constructed from k linearly independent code words. Okay, so for a given generator polynomial g of x, a lot of generator matrices can actually be formed, but the simplest one is by multiplying your g of x by x until x to the k minus 1. Okay, so for example, if your generator polynomial is given as g1 of x, that's x cubed plus x squared plus 1. Okay, so x cubed plus x squared plus 1 is 0, 0, 0, 1, 1, 0, 0. Sorry. Let me just fix that. So that's 0, 0, 1, x to the 6th, x to the 5th, x to the 4th, sorry, this is 0, x cubed, x squared, x, and 1. Okay, so if you multiply it by x, then you are shifting the polynomial by 1 bit to the left. So that would be 0, 0, 1, 1, 0, 1, 0. And you're also doing it with x squared, 0, 1, 1, 0, 1, 0, 0, and another one, 0, oh sorry, okay, 0, 1, 1, 0, 1, 0, 0, 0. Okay, and you get the 7, 4 generator matrix from the code that we used earlier. Okay, so this is that code right here. So this method, however, does not necessarily form a systematic code, as you see here. Okay, so the generator matrix does not have the structure that we need, so we can say that the code is systematic. So recall that the structure should look like this. Okay, so your IK is the identity matrix and some parity generator matrix rather right here. So let's just review a little bit from the example. As you can see, Okay, let me just clear all the clutter. So as you can see here, the first 4 bits of the code words does not necessarily translate to the 4 bits of the message. So this method of producing cyclic codes, the one where we just multiply the message by g of x, does not generate a systematic code. Oops. Right here. Does not necessarily form a systematic code as you see here. Right. So how do we make systematic cyclic codes first? Okay. So to make systematic cyclic codes, recall that the generator matrix should have this structure. Right. And as you see, since it's an identity matrix right here, we have an identity matrix right here. The first row would look like 1, 0, 0, something, until it's 0, until we enter the parity check matrix, which is, well, some random values. Right, so it's either 0 or 1. If we represent the first row as a polynomial, then your polynomial from the first row is equal to x to the n minus 1 plus some x to the n minus 1 plus some, well, let's call it r sub 1 of x. So we don't know, it depends on the parity check matrix. So in generalizing that, the nth row of your generator matrix is equal to this. Okay? And how do we obtain this form using the generator polynomial? How do we generate the cyclic code words and make them systematic? Okay? So this form can be obtained by dividing this given row by g of x. If we divide this row by g of x, since this row is a valid code word, recall that this is for a systematic code, each row of your generator matrix is a valid code word. If we divide this row by g of x, the coefficient, the remainder should be 0. Okay, so if we divide that, so x to the n minus l divided by g of x plus rl of x divided by g of x. So let me just write that down. We arrive with some quotient. Sorry. If we divide, rather, this is not, let me repeat that. Sorry, I apologize. If we divide x to the n minus l by g of x, we have a quotient plus some remainder rl of x divided by g of x. Okay, so if we divide x to the n minus l, we can actually generate rl of x. If we add rl of x to the division x to the n minus l divided by g of x, if we add rl of x to x to the n minus l and divide that by g of x, the same rl of x that you'll get from getting the remainder of this division. As you can see, if you add that remainder and divide it again by g of x, you'll get some quotient ql of x. Okay, and this x to the n minus l plus rl of x satisfies the property of the cyclic code that your valid code word must be divisible by the generator matrix g of x. Okay, so that's how you generate a systematic cyclic code word. So the generator matrix, the rows, can be determined by dividing the different degrees or different powers of x by g of x and getting the remainder, adding that remainder to them, okay? And this creates the rows of a systematic generator matrix, which creates a systematic cyclic code. Okay, and these are the steps for your generator matrix to be derived. So you can derive them. So for example, let g of x be equal to x cubed plus x squared plus 1. Determine the 7, 4 systematic code generator matrix. So to do that, you do long division for different powers of x. Okay, so the first row would be, since it's a 7, 4 code, the first row will be determined by x to the 6th. So you divide x to the 6th by the generator matrix. So the first quotient here is x cubed. So x cubed multiplied to this is equal to what you see here. And you add x to the 6th with x to the 6th. This will cancel out. So you're left with x to the 5 plus x to the 3. And to get that, you need x squared. Multiply that with this one. You'll end up with this. Add x to the 5th. It'll cancel out. You'll be left with this. Okay? And you can still divide this polynomial by this polynomial. So you add x here. Okay? Multiply it by this. You get this. Cancel. X to the 4th cancels out. X cubed cancels out. You'll be left with the remainder. This is r1 of x. X squared plus x. And your row 1 will now be equal to x to the 6th plus x squared plus x. And that will be 1 x to the 6th, x to the 5th, x to the 4th, x cubed, x squared, x, and the constant. Okay, so this will be the first row of your systematic generator matrix. So you repeat that with all other powers until you reach x cubed. Okay, so the quotients will be successively, it will be like this with the corresponding remainders. Okay, and you complete the polynomial. Okay, and you'll get the different rows of your generator matrix. So this is the 7, 4 cyclic code generator matrix. Okay. Okay. So now, using that information, how do we generate a systematic cyclic code? Okay. So to generate a systematic cyclic code, you just need to repeat what you did here. Okay, how? Your u of x first, there you go. Your u of x first must be multiplied by x to the n minus k. So this is the shifting. So it will result into this. Okay. Then we are going to add some r of x such that this multiplication, okay, will be divisible by g of x. Okay, so this multiplication by x to the n minus k ensures that the first k bits of your code word is your message. Okay, and then you add some r of x, which represents the parity bits. Okay, by getting the remainder of this with g of x. Okay, get the remainder of this, so you divide x to the n minus k times u of x by g of x, get the remainder from that. And you add these two together, you create your valid code word. Okay, so now this code word is linear and systematic at the same time. You have now created a systematic cyclic code. Okay, so it's linear, systematic, and it's cyclic. Okay, so the algorithm to do that, first step, multiply your message polynomial by x to the n minus k and get the remainder when you divide it by g of x. Then you add that remainder to x to the n minus k times u of x. Okay, so just some note before we end this part of the lecture. We call h of x and g of x orthogonal polynomials, since if we multiply them, they result to x to the n plus 1. Okay, so we'll leave this example for the next meeting, for next part of the lecture, rather. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.